Hello everyone and welcome to this presentation on matrix LED drivers. Should you make or buy? My name is Aaron Reynoso, Lumissil Microsystems Director of Analog Products for both USA and Europe. Lumissil is headquartered in Milpitas, California. Today, I will be discussing the benefits of buying a dedicated matrix LED driver versus building your own. But first, let's review some background on matrix drivers, where they are used, and how they operate. An array is necessary whenever the number of LEDs exceeds the count of 36. Supporting a greater number of LEDs requires more package pins and therefore a larger package which takes up more PCB space, consumes more power, and increases the driver cost. In this presentation, we'll review the features of a matrix driver. With this knowledge, you'll be able to help your customer decide whether to make or buy a matrix driver. Typical applications for matrix drivers are in RGB gaming keyboards where each key has its own color. Another is appliance control panels for displaying operational status. The appliance user interface has traditionally been mechanical, requiring physically turning of knobs or pushing buttons. This interface got more complex with the introduction of the microcontroller, which enabled even more functions. A simple mechanical interface cannot keep up with the additional functions of sensing, process control, and cycle times. A well-designed user interface, sometimes called a human-machine interface, or HMI, simplifies the management of this massive amount of control information. A typical LED-based interface consists of low-power LEDs configured to drive 7-segment displays, individual color, or icon backlighting. An HMI not only allows the user to configure the appliance, it also displays the status. The microcontroller is expected to not only monitor the appliance motors, sensors, button inputs, but also display the status. The microcontroller can easily be overloaded. A matrix driver will offload the display status function. Now, let's discuss the basics of a matrix array. So what is considered a matrix? Well, a matrix is an arrangement of items in row and column format such that any item can be identified by its row and column position. In this slide, there's only one true matrix. It is the 2x2 arrangement. The other 1x1 or 1x2 arrangements stretch the definition of a matrix since there is no requirement for both row and columns. The 2x2 arrangement shows the complexity of a switch selection between LEDs in a row and column arrangement. Let's go deeper. In a matrix format, LEDs are wired together in rows and columns to create a 2x2 array. This reduces the number of required package I/O pins. For example, driving 64 LEDs would require 64 I/O pins since each LED needs its own I/O pin. However, by wiring all the LED anodes in groups of 8 to create 8 rows of R1 to R8, and all the cathodes in groups of 8 columns of C1 to C8, the required I/O pins is reduced from 64 to only 16. In a true matrix arrangement, each LED can be addressed by referencing its own row and column location. For example, the highlighted LED is addressed by enabling row 1 and column 4. In this matrix, the row switches power the LEDs and the column switches provide the constant current sink. Therefore, turning on a specific row powers 8 LEDs, while the column switches provide a current sink path for one or all of the 8 row LEDs. Now, let's review how a matrix LED driver functions. In a matrix arrangement, the LEDs must be driven in a multiplexed scanning sequence. This means a row is on for a short duration before it is turned off, followed by the next row in the sequence. This row on-off sequence continues until the last row, in this case row 8, and then the sequence starts all over again with row 1. This procedure is known as a scan timing, and a scan cycle is the total time required to complete one row sequence. There are many advantages to using a matrix scanning architecture. One benefit is a reduced current draw, since all the LEDs in the array are not on at the same time. Also, since the number of I/O pins is reduced, the package size is reduced. With a smaller package, the IC driver cost is reduced, and the PCB footprint area is also reduced. An added benefit is the reduction in MCU overhead, since the driver handles its own scan timing and LED dimming. The micro only needs to configure it with a simple bus interface. The MCU overhead is further reduced if the matrix driver integrates LED-specific functions such as current adjustment, error detection, color mixing, matrix deghosting, etc. However, there are some disadvantages to a matrix driver. The biggest disadvantage is the LEDs do not appear as bright as expected. This is because a row is on for only a short period of time, resulting in what is known as LED average brightness. Since the LED is on for only a short time, we tend to average out the brightness level based on the on time over the complete scan cycle time. Another potential issue with matrix scanning is the scan frequency could contribute to EMI. This is because the rows are constantly turned on and off at a specific frequency, resulting in possible overshoot and undershoot, which could generate EMI spikes. Finally, it should be noted that device thermals will be doubled since the row FET thermals need to be added to the current sink thermals. Now, let's make the LED matrix do some work. Now, let's discuss practical uses for an LED array. The usefulness of LEDs in array format is limited to scrolling text or displaying an image. However, the goal of a control panel is to spread out the status information about the panel interface. Partitioning the array to perform status information on a control panel expands the usefulness of a matrix driver. For this example, consider a 7-segment common anode display which consists of 8 LEDs. In our 8x8 array example, the rows connect common anode LEDs, making it easy to partition and drive 4 7-segment displays. Next, 3 consecutive LEDs in a row can be partitioned to perform an RGB function. This is because when a row is enabled, the common anode RGB LEDs are powered, and the column current sinks perform the PWM for color mixing. These RGB LEDs can be used for backlighting icons to indicate color status information. Finally, the remaining 20 LEDs could be used for driving individual LED status. And now let's review how the MCU controls the entire 8x8 array using a simple I2C or SPI interface. As discussed before, the MCU can control any of the LEDs in the array by selecting its row and column location. Each LED in the array has its own set of hardware registers for PWM, breathe operation, current adjust, open short status, or simply on-off configuration. The Lumissil matrix drivers integrate auto-addressing technology, which enables the entire 8x8 array or portions of it to be software accessed and configured using array programming techniques. The following is an example of a refrigerator control panel for which we will provide both a discrete matrix design followed by a matrix driver solution. This control panel has two 7-segment displays and many icons for a total of 144 LEDs. These LEDs will be driven by a 9x16 matrix. First, let's discuss making your own 9x16 matrix driver. For the discrete or make your own approach, a 9x16 matrix driver is created using 9 FETs for the rows and a 16-channel serial to parallel shift register for the columns. Note, there is no current regulation. Here the micro takes on the responsibility for array scan timing by driving the FET on time and sending data to the serial shift register to sync the columns. This approach works and has been used by control panels for many years, but with hidden performance costs. Requiring the micro to perform scan time and pushing data to the array consumes resources which could best be utilized performing sensor management or appliance calculations. Of course, a high-end micro will have plenty of bandwidth to accomplish scan timing plus other functions, but this comes at a higher cost. This discrete implementation will turn on/off the individual LEDs in the array, but any RGB color mixing or LED breathe effect will add to the micro's operating bandwidth. Other functions missing with a discrete approach is deghosting, individual LED current adjust, LED error detection, and there is no EMI suppression capabilities. A basic discrete matrix driver shown here will provide basic functionality but requires 53 components. So now let's look at the same 9x16 LED application using a modern matrix driver IC. The previous slide showed a discrete implementation of a 9x16 LED matrix to support 144 LEDs partitioned for two 7-segment displays and 123 individual LEDs. In this slide, the Lumissil IS31FL3741A matrix driver is used to replace the discrete implementation for supporting the same LED partitioning as before. As previously discussed, the dedicated matrix drivers have many advantages over the discrete implementation. So let's review them. First, notice the matrix driver is configured to have only 4 column switches. This results in a higher LED average brightness of 1/4 versus the discrete's average brightness level of only 1/9. Next, the microcontroller overhead is highly reduced. The required GPIO count reduces from 13 in the discrete to only 3 for the I2C bus support. Typically, the micro already has an I2C bus used for other components and can be shared with the matrix driver. More importantly, the micro software overhead is reduced since the LED driver integrates functions such as PWM to offload the micro. With a lower pin count requirement and less software overhead, a lower cost micro can be used. Finally, notice the component count is reduced from 53 to only 17 when using a matrix driver. A lower component count not only increases the control panel reliability, but it could also lower PCB assembly costs by reducing the PCB size and/or requiring less PCB layers. Now let's look at another example, and let's use a feature-rich LED driver, a matrix driver that integrates capacitive touch switches. Kitchen appliances typically favor capacitive touch switch inputs over raised mechanical switches because they can be easily wiped clean. Therefore, having a matrix driver with capacitive switch inputs further simplifies the control panel display. Lumissil has the IS31FL3800 family of drivers, which supports 11 touch switches and either 72 or 128 LED size arrays. The next slide shows a control panel application which utilizes the IS31FL3800 to support a 45 LED display and 11 capacitive touch switch inputs. This user interface is for a kitchen blender. It has a 2-digit 3x5 LED array which can display text or numbers. It also has 11 capacitive inputs with LED backlighting for function and status purposes. 11 capacitive switch inputs and 45 LEDs are used. The next slide shows a schematic for this circuit. Notice the entire Blender Appliance user interface can be implemented using a single IS31FL3800 matrix and capacitive switch input driver. Few discrete components are required. An LED matrix driver such as the IS31FL3741A discussed earlier integrates many features not possible to do in a typical discrete matrix implementation. One important feature found in Lumissil matrix drivers is a deghosting function. A ghost is any weird pixel, artifact, or glitch that appears randomly in an LED array as shown here. This is a result of stray capacitance in the array wiring that discharges through an LED which should be off, but instead becomes dimly on. Deghosting technology periodically discharges any stray capacitance to avoid this ghosting effect. We already discussed how the MCU software and hardware overhead is reduced with a matrix driver. Other functions such as PWM engine in the matrix driver further offloads the MCU since the MCU no longer needs to send out row and column updates to a specific LED which requires a PWM value. Similarly, LED open and short detection technology integrated in the matrix driver simplifies MCU overhead since the MCU only needs to read a register. Finally, a matrix drive saves on PCB area and increases reliability. These are all advantages which cannot be duplicated with a discrete implementation. So, let's revisit the question. Should you design your own or buy a matrix driver? While it is possible to make a discrete matrix driver, it will be lacking many advanced functions. It will require more components, and it will require more PCB area. I hope I was able to convince you that a matrix driver has many advantages over a discrete solution. Among them is freeing up the MCU so it can focus on other functions such as monitoring sensors, controlling motor or relays, and of course performing algorithm calculations. A matrix driver also facilitates the implementation of LED lighting effects and integrates many key functions such as deghosting. Advanced drivers even integrate capacitive touch for making smart, elegant user interfaces. It really does make more sense to use Lumissil matrix drivers. And now we come to the end of the presentation. Thank you for your attention. Do you have any questions? If you do, please feel free to send me an email anytime to discuss your matrix LED driver requirements. Thank you again for your attention.